Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. In this video, we will start a new chapter, chapter 4, the medium access control sublayer, or in short, the MAC sublayer. Now, in the previous videos, we finished two chapters. We finished the introduction chapter and we finished the data link layer chapter. Now, here in this video, we will introduce the third topic in this course, medium access control sublayer. And in the context of our textbook, this corresponds to chapter 4 of our textbook again, medium access control sublayer or MAC sublayer. Before we go into the details, let's have a bit of a motivation. So in the introduction, we know that we have two types of networks. In general, we can classify networks into two general categories: point-to-point networks that use point-to-point links, and broadcast networks that use broadcast links or broadcast channels. What is a broadcast network? It is a network in which all stations are using the same communication medium. All stations connected to the network are using the same communication channel or the same link or the same communication medium, whether all these stations are connected to a common cable or these stations are connected to a common ring cable, or all these stations are interconnected using a wireless communication channel which is shared between all of them. At the end of the day, a broadcast network has only one communication channel which is used by all. As we mentioned in the introduction, what is the main problem that arises in broadcast networks? It is the multiple access problem. It is the problem of collisions or interference between different transmissions if two stations are sending at the same time. This is a problem that needs to be avoided, and this is what we call the multiple access problem, and techniques that avoid that are called multiple access techniques. In terms of the layers, and we talked about the layers in chapter 1, whether the Open Systems Interconnection Reference Model, the OSI reference model, or the TCP/IP reference model, we said that network functionalities are grouped as a number of layers. So we have the physical layer at the bottom, layer 1, physical layer, followed by data link layer, followed by network transport, and so on, until we have the application layer on top. Now, the question is, which layer is responsible for implementing multiple access techniques, techniques that avoid collisions, techniques that organize transmissions in a broadcast network that have a shared communication medium? It is basically the data link layer. So in general, the data link layer is responsible for solving the multiple access problem, or that's the layer responsible for implementing multiple access techniques that organize who transmits when so that we avoid collisions. But to be more precise, it is not the data link layer as a whole, but it is a special sub-layer of the data link layer that is called the medium access control sublayer, or in short, the MAC sublayer. So to be more specific, if you have a broadcast network, then the data link layer has a sublayer. Part of the data link layer, or a sublayer of the data link layer, is called the MAC sublayer, medium access control sublayer, and this is the sublayer responsible for solving the multiple access problem. Now, before we go into specialized multiple access techniques that are used in computer and communication networks, let's review the standard techniques for avoiding collisions, or the conventional methods for avoiding collisions or organizing transmissions. So we can talk about frequency division multiplexing, or FDM. In FDM, frequency division multiplexing, the channel bandwidth in hertz, so the frequency range that can be supported by our communication channel, is divided into sub-channels. So if we know that we have n users using the network, we divide our channel bandwidth in hertz into n equal sized frequency bands, right? So that we can allocate or assign to each user a specific frequency band that don't overlap. So in other words, user 1 gets frequency band F1, user 2 gets frequency band F2, user N gets frequency band Fn. So all users could send at the same time, but using different transmit frequencies, so we don't have collisions, simply because these transmissions are each sent at its own frequency. Now, this works very well, but it's not efficient in a number of ways. First of all, imagine that after this allocation or this assignment has been done, so the channel has been divided into n frequency bands, and then users got assigned their own distinct frequency bands. Now we have a new user that wants to use the network. So what can we do? That user needs to be blocked in this case. It will be prevented from using the network. Otherwise, we have to redo the whole allocation or whole assignment again. It is also not efficient even if you assume that the number of users in the network remains fixed. Using FDM is not efficient in case that one of the users doesn't have anything to send. So imagine we have n users and each user has a frequency band. Now I'm one of these users, and during some time I have nothing to send. I don't have any frames to send. I don't need to send any frames. It means that this frequency band that belongs to me will be idle during this time, and the other users are not able to use that frequency band because it belongs to me, right? And as you have noticed, that inefficiency comes from the fact that this channel allocation, assigning different frequency bands to the user in an FDM style, is basically static. So the situation is fixed. I have a frequency band, and that assignment does not change with time. It does not change with different network conditions and different user needs. The same inefficiency also applies to time division multiplexing, or TDM. TDM, or time division multiplexing, works differently. However, it has the same inefficiency. So in TDM, time division multiplexing, we divide our time into time slots. So in general, time is divided into slots, and then we allocate slots to the users. So user 1 gets slot 1, user 2 gets slot 2, user 3 gets slot 3, and so on. User n gets time slot n, and then these stations, basically these network users, will take turns. So in the first time slot, user 1 sends a frame. In the second time slot, user 2 sends a frame, and so on. In the last time slot, user n sends a frame, and then we go back to start from slot number 1, and so on. So basically, time division multiplexing means the stations will take turn in transmission. However, that allocation is still static. If I have a time slot, usually that time slot doesn't change. So why is that inefficient? Again, the same inefficiency. If we assume that the number of users is fixed and during my time slot I have nothing to send, it means that during this time the network will not be carrying any information because the other network users are not able to use my time slot. And if you imagine that we have a new user that basically requests to use the network or be admitted into the network, that user needs to be blocked because we don't have an available time slot. That's why, to solve the inefficiencies that come from static channel allocation, we have some specialized mechanisms that are used in computer and communication networks, and we start with the two most famous ones, Aloha and Carrier Sense Multiple Access, which is known as CSMA. Aloha is a little bit older. It was invented first, and then Carrier Sense Multiple Access came after that. It's of course old nowadays as well, but CSMA, Carrier Sense Multiple Access, is part of the standard already. So in the Ethernet standard, which is a standard for building local area networks using wires, that Ethernet standard is using Carrier Sense Multiple Access as part of the whole standard. Now let's basically try to describe these two so that we can talk about something more specialized for wireless networks, and this will come later. So how does Aloha work? First of all, Aloha was developed at the University of Hawaii by Norman Abramson and his colleagues. Norman Abramson and his colleagues at the University of Hawaii introduced the Aloha technique. Aloha means hello in the language of Hawaii, and that's why the technique was called Aloha. What was the motivation? You know, the University of Hawaii exists in the state of Hawaii, which has multiple islands. So that university has a main campus in the main island of Hawaii and other campuses on the other islands of Hawaii. So the university wanted to come up with a technique basically for a methodology to exchange packets, to have a wireless network between the different campuses on the islands together with the main campus on the main island. So they developed a technique called Aloha. And as you will notice, it is a multiple access technique. It allows different stations to start exchanging messages while basically avoiding collisions and while they are all using the same frequency band. So we are not allocating the channel bandwidth into sub-frequencies or anything. No, stations are all using the same frequency band, and at the same time using that Aloha methodology, that Aloha protocol, stations can still attempt to avoid collisions as much as possible. So how does this work? To begin with, let's state here that we have two versions of Aloha. So Aloha comes in two flavors, or in other words, Aloha has two versions, pure Aloha and slotted Aloha. Let's start with pure Aloha. Now that protocol is really easy to state. And then after that, once we understand it, we will spend some time trying to understand how it performs. So some performance analysis, and we will see some derivations of our equations and so on. But let's start with just describing the protocol. How does Aloha work? Imagine that we have a common communication channel, so a common link that all stations connected to the network are sharing. And if a station would like to send a frame, now if a station has a frame to send, according to Aloha, that station would just send the frame. If you have a frame to send, just send it without coordination, without asking anyone for help, and even without having a network controller that would make a decision on behalf of the other stations. So these mechanisms here that we are covering, Aloha and CSMA, they are decentralized or distributed in the sense that there is no central manager that basically decides who gets to transmit at what time. No, the stations will make their own decisions in terms of when to transmit and when not to transmit, and as much as possible avoid collisions. Again, going back to Aloha, how does Aloha work? We're all stations connected to the common channel, to the common link. If a station has a frame to send, it sends the frame. Now we have two possibilities. The frame gets delivered successfully if there is no collision. If by chance nobody else, during that time, nobody else is attempting to transmit anything else, right? Any other frame, it means that my frame will arrive successfully. And I will know that, the sender would know that by receiving an acknowledgement from the receiver, right? So this is the first possibility. The second possibility is that a collision occurred because there is another station that attempted to transmit during my transmission. So we get a collision. It means that my transmission will not be successful, and I would know that because I will not get an acknowledgement from the receiver. The receiver will not send an acknowledgement, and if I time out before receiving the acknowledgement during this timeout period, I will know that my transmission was not successful, most likely because of collision. What do I do in this case? What does the station do in this case? Wait for a random amount of time and then attempt to send the same frame again. This is the key. Let me repeat quickly and then try to justify why is waiting a random amount of time useful. Again, what is Aloha, or in other words, pure Aloha? How does Aloha work? How does the Aloha protocol work? If you imagine that we are all stations connected to the common channel, to the common communication medium, if you have a station that has a frame to send, that station would send the frame immediately. If the frame arrives successfully, and the station would know that from getting an acknowledgement, the station will be happy, okay, that frame got delivered. If it sends again, it will be a new frame that it needs to send maybe later, right? The other possibility is that the frame transmitted will go through a collision, will experience a collision because someone else was sending at the same time. And how will the station know about that? From not getting the acknowledgement during the timeout interval, during the timeout period. It means that a collision happened, and in that case, the original station that attempted to send the frame will wait for a random amount of time and then retransmit. So it will back off for a random duration and then come back to transmit again. Now, why do we wait for a random amount of time? Imagine that I'm a station. I just sent my frame. You are another station, and at the same time, you have a frame also that you would like to transmit. According to Aloha, both of us will transmit without coordination, without asking anyone, and now we will get a collision. Both of us will basically find out about the collision later by not getting the acknowledgement. Now, if this happens, if we know that our transmission was not successful because of a collision, what will we do in this case? According to Aloha, each one of us will wait for a random amount of time. So using a random number generator, I will just decide on a random amount of time. Let's say I will decide to wait for 3.5 seconds, and you decide to wait for 4 seconds, and then we start again attempting to transmit. Since we are waiting for a random amount of time, even though we transmitted the first time together by coincidence, by chance, it is not likely that we will transmit the second time together as well. So that's why we are trying to avoid the collision. That's simply how Aloha works. Very simple to state. If you have something to send, you will send. If a collision happens, you will wait for random time, and then you will attempt to send the same frame again. If there is no collision, you will just be happy and you will wait for the next attempt until you want to send something new. Of course, collisions are detected by acknowledgements or lack of acknowledgements. Now, how does Aloha perform? How can we assess the performance of Aloha? I think you just noticed that Aloha is very simple. If you have something to send, you will send. If there is a collision, then you will wait for random time and then you will send again, without any coordination with anyone else and without any centralized decision basically on behalf of the stations connected to the network. So to be able to understand the performance of the Aloha protocol that we have just described, we need to make two definitions. So first of all, we define the offered load that we give the letter G, that we give the symbol G. What is the offered load? It is the average number of attempted frames, the average number of attempted transmissions by all stations connected to the network per unit time, the average number of frames, new and retransmission together, and by all stations. So if we say G is equal to 10, it means that on average, all stations connected to the network are attempting to transmit 10 frames per unit time. And to be more precise, we take the unit time to be the same as the frame time. So the frame time is the actual time that the frame needs to be in the network until it arrives at the destination. So it is basically the delay that the frame will stay in the network until it arrives at the destination. If we say the frame time is equal to 1 millisecond, it means that if I send the frame, it will take 1 millisecond until that frame arrives at the destination. Okay, so we take that frame time as our unit time. So if we say the offered load G is equal to 0.8, it means that on average, all stations are attempted to transmit 0.8 frame in every millisecond, which is the frame time. Now, what is the throughput S that we give the letter S or the symbol S? The throughput is not the average number of attempted frames. It is basically the average number of frames successfully delivered per frame time, in every frame time. Again, to imagine this frame time well, let me use the same example. Imagine that it takes 1 millisecond to deliver a frame. So if I'm the only station connected to the network, I don't have any competition from the other stations. If I'm the only station connected to the network and I'm sending a frame to a receiver which is not sending, so I'm the only transmitter in the network. If I send the frame, let's say it takes 1 millisecond until this frame arrives at the destination, at the receiver. So during that millisecond, the average number of frames that get successfully delivered, this is what we call the throughput, and this is what we give the symbol S. Since we take the frame time as our unit time, it is obvious that this throughput cannot be more than 1, because at most during that frame time, we can deliver only 1 frame. Basically, if we have 2 frames that are transmitted at the same time, they will collide, and it means that both of them will not be successfully delivered. So the only case in which we have a successful delivery is the case that we have only 1 station attempting and the others are silent by chance. By coincidence, the other stations are not attempting to transmit anything during that frame time. So in that case, we deliver only 1 frame. However, if we get collisions, since there is a possibility to get collisions, we might have frame times during which we are not able to deliver anything. So imagine that, again, the frame time takes 1 millisecond. So it takes 1 millisecond to deliver a frame. So during that millisecond, if 2 stations attempt to deliver at the same time, nothing is delivered. So basically, the frames delivered during that millisecond is 0. So on average, the throughput S is something less than 1. So let me recap. The offered load, for which we use the symbol G, is the average number of attempted frames that are attempted by all stations connected to the network during 1 frame time. And the throughput S throughput, for which we use the symbol S, is the average number of successfully delivered frames per frame time. I think it's also easy to imagine that S is smaller than G. So if we attempt to transmit a number of frames, whatever gets successfully delivered is either as much as this in case we don't have any collisions, or less than that in case we have collisions. Now, how in pure Aloha, how is S related to G? It can be proven, and at the end of this video, I will actually show you a simplified or an approximate proof. It can be proven that the offered load S is equal to G e to the power of minus 2G. G is the number of attempted frames per unit time, and S is the number of successfully delivered frames per frame time, and it can be shown that for pure Aloha, S is equal to G e to the power of minus 2G. So for now, for the rest of the discussion until the proof comes, you will just believe me that this is how S is related to G. We will look at some aspects, and then at the end of the video, I will come back and actually prove this formula for pure Aloha and a similar formula for slotted Aloha. Now, if we take it as granted, if we believe that this is how the throughput is related to the offered load in pure Aloha, let's look at how the curve or how this function looks like. So if you put on the x-axis G and on the y-axis S, again, G is the average number of attempts per frame time, and S is the average number of successfully delivered frames per frame time that we call the throughput. Now, let's just draw this function mathematically, without physical meaning. Let's put G equal to 0. When G is equal to 0, S becomes 0 as well, right? 0 times e to the power of 0, which is 1, so we have 0 here. So when G is equal to 0, S is also equal to 0. That's why we have the point at the origin, 0, 0. Now, if you try to substitute with different values of G, so if you take increasing values for G, 0.1, 0.2 until 0.5, you will notice that S will increase with G. S will increase, but let's try something here. When G goes to infinity, when G, the offered load, goes to infinity, let's substitute. If you substitute with infinity, that term gives you infinity, and the other term gives you 0. So infinity times 0, which is an undefined quantity, infinity times 0 is undefined, exactly like infinity over infinity and 0 over 0. If you want to be more comfortable with this, you can also rewrite G times e to the power of minus 2G as G divided by e to the power of 2G. So this formula here is equivalent to G divided by e to the power of positive 2G. So when we substitute with G equal to infinity to get the limit, you will get infinity divided by infinity. And to get the limit, we can use L'Hopital's rule and get the derivative of the numerator and denominator. If you do that, it's very easy to find that when G goes to infinity, S goes to 0. So when G goes to infinity, S goes to 0. As long as we start from 0 and we end with 0, it gives rise to the fact that actually the throughput goes up and then comes down. And simply, if you try to substitute with different values for G, increasing values 0.1, 0.2, 0.5, 1, 1.5, and so on, you will find that S basically follows this curve. The throughput goes up and then it goes down. This is mathematically by observing this function here. However, does this make sense? Like, is this basically, does it make sense from the physical meaning point of view? Yes, and I would like to convince you with that. What is G again? G is the average number of attempted transmissions. If G is equal to 0, it means that all stations in the network are not attempting to transmit anything. Nobody is attempting to transmit any frame. Obviously, in this case, we're also not delivering any frames. In that case, S is equal to 0. Now, when S increases, when G increases, it means stations are attempting to transmit more. It makes sense to imagine that the throughput will also increase. So I start increasing my attempts. It means that my successful deliveries will also increase until a point where we have too many attempts. Too many attempts means also more collisions. And if we have more collisions, it means that the number of successful deliveries, the throughput will go down again. And imagine that we have infinitely many attempts. So per frame time, we have infinitely many transmission attempts by the stations connected to the network, which means that everything will collide for sure, and we have no successful deliveries. That's why the S goes down to 0. So this curve here represents the throughput on the y-axis versus the offered load on the x-axis. Now, since the throughput is going up and then coming down, so this suggests that we have a maximum throughput. And the next question is, what is this maximum value? Basically, it can be shown using simple math that this maximum value is at 0.18. So this maximum value here is at 0.18, which tells you that the maximum possible throughput in pure Aloha is 0.18. Or in other words, 18% is the maximum possible success rate. So if we're attempting to send frames, the success probability is 18%. Of course, that's not high, but I think it is justified because the method is very simple and we're not coordinating. If you have something to send, you will just send it, and so on. Let's see where this 0.18 is coming from. So that's why I have my own illustration here. How can we calculate the maximum throughput? So in pure Aloha, again, how was the throughput related to the offered load G? So S as a function of G is equal to G e to the power of minus 2G. As if we have a function Y as a function of X. If you have a function Y as a function of X, how can you calculate the value for X which makes Y maximum? In other words, what is the value for G that makes S maximum? Obviously, to do that, we have to get the derivative of S with respect to G, ds by dg. After getting the derivative, we set it equal to 0. So when the derivative is equal to 0, it means that our function S has a horizontal tangent, right? Which means that we have a maximum point. A horizontal tangent, or the slope of the tangent, becomes 0. You know all from basic mathematics or university level mathematics that if the derivative of a function becomes 0, it means that we have a maximum or a minimum point. In this case, it's a maximum. Basically, distinguishing between the maximum and the minimum point can be done by getting the second derivative. But in our case, we have a maximum point in the function here. So let's get the derivative. The derivative of this function, we have G e to the power of minus 2G. Our function is actually a product of two functions, G and e to the power of minus 2G. So to get the derivative, it is the first times the derivative of the second, and the derivative of e to the power of minus 2G is the same, e to the power of minus 2G, times the derivative of the exponent, which is negative 2. That's why we have negative 2, plus the second as it is, e to the power of minus 2G, times the derivative of the first, which has a derivative of simply 1. So we have this term plus that term equal to 0. Luckily, we have e to the power of minus 2G in both. So if we imagine that we divide the whole equation by e to the power of minus 2G, it means this will cancel. And the equation becomes minus 2G plus 1 equal to 0. By organizing terms, 2G is equal to 1, or G is equal to half. So this tells you when the offered load G is equal to half, the throughput is maximum. So basically, when the number of frames attempted by all stations is 0.5. So in every frame time, again, for simplicity, imagine that the time needed to transmit a single frame is 1 millisecond. If in every millisecond, the number of attempted frames by all stations is 0.5, so we are attempting only 0.1 transmissions in every frame time. Or in other words, every 2 frame times, the stations are attempting only 1 transmission. In that case, in pure Aloha, the throughput becomes maximum. Now, this tells us the value for G at which S is maximum. But the other question is, what is the value of this maximum S itself? What is the value of this maximum S itself? And this can be obtained easily by substituting that G, which is 0.5, in the S equation. So when we substitute here, we have a half times e to the power of minus 2 times half. So half times e to the power of minus 1, 1 over 2e, which is 0.18. E is the famous Euler constant, so 0.18. And this is what you see here. So the best channel utilization we can hope for in pure Aloha is about 18%. This is pure Aloha. Now, a slightly modified version of Aloha is called slotted Aloha, and we're just doing a small trick that improves this throughput. Basically, it doubles the throughput from 18% to 36%. So what is slotted Aloha? Slotted Aloha simply works as follows. Before we mention anything about what the stations do, slotted means that our time in general, time is divided into discrete time slots. Imagine that we have a clock that tick. So we have tick number 1, tick number 2, tick number 3. So we have time slots, we have discrete time slots, and a user is allowed to transmit only at the beginning of a time slot. So imagine that we have time slots at time 0 and at 1 millisecond and at 2 milliseconds and at 3 and 4 milliseconds and so on. If at 0.5 milliseconds at time equal to 0.5, if I have a frame to send, I cannot send it right away. This was pure Aloha. I cannot send it right away. I have to wait until the beginning of the next time slot, which is at 1 millisecond, and then I can start transmitting the frame. Again, this is what slotted means. So how does slotted Aloha work? It works as follows. Imagine, again, the same situation where all stations connect to a shared communication channel. If I have something to send, I will send it at the next time slot, immediately at the next time slot. Not immediately right now, but immediately at the next time slot. So this is what I do. Now, if my transmission is successful because nobody else was sending by chance and I'm not getting any collision, it means that I'm done and I can focus on future transmissions. If my if my frame transmission is not successful due to a collision, and I will find this out by timing out without getting any acknowledgement from the receiver, what I will do is that I will wait for a random time. However, the random time becomes discrete as well here. The random time is a random number of time slots. So I will back off and wait for a random number of time slots, 6, 7, 8, 10, 12 time slots at random, and then I will transmit again the same frame. Now, in terms of the performance, we're still using G as the offered load, the average number of frames attempted per frame time, and S is the average number of successful deliveries per frame time. G is called the offered load, S is called the throughput. And in slotted Aloha, just by introducing this time slot, the idea of having time slots, just by organizing transmissions, is that basically stations still decide on their own. But instead of starting the transmission at any time, no, they can only start transmissions at the beginning of the time slot. By doing that, it can be shown that the throughput S is given by G e to the power of minus G. So we don't have this 2 in the exponent. We don't have the 2 in the exponent, and S is given as G e to the power of minus G. How does this look like? In general, the general shape is exactly the same. So when G is equal to 0, S is also equal to 0. And even in this formula, when G goes to infinity, S also goes to 0. And in between, we have a maximum value. However, the curve is higher. The entire curve is higher because we don't have this negative 2 here. G e to the power of minus 2. G is for pure Aloha. G e to the power of minus G only is for slotted Aloha. It is the similar trend. Again, if we don't attempt anything, it means we're also not delivering anything. That's why we have the point starting at 0 here, at y, at s equal to 0. And when we go to infinity, asymptotically, the throughput also approaches 0. However, in slotted Aloha, the whole throughput curve is on top of the pure Aloha throughput curve. G e to the power of minus 2G versus G e to the power of minus G in slotted Aloha. And again, in this curve, we have a maximum point, and we can get it in exactly the same way. So how can we get the maximum value in slotted Aloha? Simply by taking this function and getting the derivative. It follows exactly the same, but we don't have the minus 2. And it is very easy to verify that the maximum G, or the G at which S is maximum in slotted Aloha, is actually 1. So when G is equal to 1, S is maximum. And to get the actual value for S, which is maximum, we simply substitute here with G equal to 1. So 1 times e to the power of minus 1, which is simply 1 over e to the power of minus 1, or 1 over e, which is 0.368. So basically, the efficiency is about 36.8%, which is double that of Aloha. So just by introducing the idea of having time slots, which further organizes transmissions, in a sense, the throughput or the maximum efficiency is doubled from 0.18 to 0.36. Now, let's try to understand Why is this? So why does slotted Aloha have a higher throughput? So let me start by an intuitive argument that will justify why is slotted Aloha doing better than pure Aloha in terms of throughput, in terms of the channel utilization or the success rate, 36.8% versus 18.4%. Intuitively, basically, we can establish this argument as follows. We establish the argument using the concept of the vulnerability period. So what is the vulnerability period? To understand the meaning of the vulnerability period, let's assume that we're all stations connected to a network, and that network has a common communication channel. Like in the wireless network, we have one wireless channel, and if we send, basically we are sending on the same channel. So if two stations are sending at the same time, if there is an overlap between two transmissions in time, it means that we get a collision. Now imagine that I'm sending my frame. So to understand this better, let's just assume some times. So this is time little t here, an arbitrary time in which I start sending my frame. The next time is t plus capital T. The next time is t plus 2 capital T. The time before little t is t minus capital T. So we assume in this example that the frame transmission time is capital T. If I send the frame, it will exist on the channel for capital T seconds or milliseconds, and then it will arrive at the destination. So at that time, t plus t, my frame is not on the channel anymore. So if I start sending at little t, it means that my frame will exist on the channel until t plus capital T, and after that the channel is idle again, and others can start transmitting. Now, what is the vulnerability period? The vulnerability period is that time duration. It is the time period during which other stations, if they send the frame, that frame can collide with my own frame. So again, the easiest way to understand it is to assume that I send my frame already at time little t. And because we assume that all frames have a delay of capital T, it means that my frame will exist on the channel. This is a timing diagram. So you can assume that we have an axis here representing time. So different things happening at different times. I start sending my frame at time little t, which means my frame will exist on the channel until t plus capital T. Now, let's consider other stations and other transmissions. If another station, this is my frame, let's say you, one of the other stations, start exactly sending at t minus t here. Start exactly sending at t minus t. And for simplicity, we assume here that all frames have the same length, which means they have all the same delay or duration, capital T. If you start transmitting exactly at t minus t, it means your frame will exist on the channel between t minus t, time, and time little t, which means that your frame will not collide with mine. Exactly at the time that yours is finished, mine will start and we don't have a collision. However, if you start transmitting a little bit later, even if that delay after t minus t is very small, epsilon or delta or any small time, you start a little bit after t minus t, it means that your frame will finish a little bit after small t, little t, which means that during this small time, during that small time, your frame and my frame exist on the channel at the same time, which means that red frame here collides with mine, even though the overlap is small. The overlap is small in time, but still during some time, both frames were on the channel at the same time, and we have a collision. Now imagine that at time t plus t exactly, another station starts transmitting. It means after mine is finished, you start transmitting and we don't have a collision. But if you start a little bit before, and this can happen in pure Aloha, because remember, in pure Aloha, frames can start to be transmitted at any time, right? So if you start transmission a little bit before t plus t, it means that we have a collision. So during that small time interval, your frame and my frame exist on the channel at the same time. Bottom line, which frames will collide potentially with mine? Frames that start to be transmitted between t minus t and t. Any frame that starts here to be more precise, a little bit after, epsilon or so after. And if it starts to be transmitted here or here and so on until that time. So any frame that starts to be transmitted by any other station between t minus capital T and t plus capital T will collide with my frame. And this is what we call that duration of 2t, 2 times the transmission delay of the frame. 2 times the transmission delay of the frame. This is what we call the vulnerability period. This is the time duration during which my frame was vulnerable to collisions, because other frames were transmitted. However, if a frame is transmitted before t minus t or after t plus t, it will not collide with my frame. So that time I'm not vulnerable. And in this time, I'm also not vulnerable. In short, the vulnerability period, or in other words, the time duration during which my frame can potentially experience a collision, is between t minus capital T and t plus capital T, which has a difference or time duration of 2 times the frame transmission time, 2 times capital T. So the vulnerability period in pure Aloha is 2 times capital T. Now, in slotted Aloha, things are a little bit different. Let's have the same setup. This is time little t. This is time t plus t. This is time t minus t. But instead of these being just arbitrary times, these are actual time slots because the channel is divided into slots. So imagine that this is a time slot. So this is the beginning of the slot, this is the end of the slot, and the beginning of the next slot. And this was the slot before, and so on. So this is a time slot here from t minus t until little t. And this is the next time slot from little t to t plus capital T. And this is the following time slot from t plus capital T until t plus capital 2t, and so on. So imagine at this slot, little t, I start a frame, so this is my frame. Now, question, what other frames will collide with mine? Imagine that you are another station, and at that time here, do you see this cross? At that time, you generate a frame that needs to be transmitted. When will you start transmission in slotted Aloha? Will you start immediately? No, you will wait until the next time slot, which means you will send exactly in my time slot, and these 2 frames will collide. This is another station. At that time, you have a frame to send. You will also send it in my time slot. If this is a third station, and at that time exactly, axis going like this again represents time. At this time, you have a frame to send. You will send it exactly in my time slot, so we will collide. However, what if a station has a frame to send here in this time? When will the station start transmission? In the next time slot, which means not with me, and we will not collide. So what about here? If another station has a frame to send here, anytime here, when will it start transmission? In this time slot before me, which means we are not colliding. So basically, any frame generated in the previous time slot, this is my time slot, any frame generated in the previous time slot will collide with my frame, but others will not collide. So the vulnerability period is only 1t. As you see, the vulnerability period is only 1t, simply because even though I have a frame at any one of these times, I start exactly at the beginning of the time slot. And if I have a frame to send at that time, I will start in the next time slot and I will not collide with this frame. And this is different from pure Aloha. So in slotted Aloha, the vulnerability period, or the time during which this frame can potentially collide with another frame, is only 1 capital T, or 1 frame delay. Now, let's compare between the two, pure Aloha versus slotted Aloha. Which one of these 2 techniques has a smaller vulnerability period? Obviously, slotted Aloha has a smaller vulnerability period. Again, the vulnerability period means the time during which a frame can collide with another frame. If this period of time is smaller, it means that the chance for collision is smaller, or the probability for collision is smaller. And if the frame has less chance to collide with other frames, it means it has a bigger chance to be successfully delivered, which means that the throughput is higher. This is the bottom line. So in short, what is an intuitive argument? That pure Aloha is performing worse than slotted Aloha, or slotted Aloha is performing better than pure Aloha. In terms of throughput, it is that argument of the vulnerability period. From these two figures, we understand that the vulnerability period in pure Aloha is 2 times T, 2 times the frame delay, and in slotted Aloha, the vulnerability period is only 1 T, 1 frame delay, and because the vulnerability period is smaller in slotted Aloha, it means that the chance for collision is less, and it in turn implies that the throughput is higher. The average number of delivered frames is higher in slotted Aloha as compared to pure Aloha. As an exercise, can you think of any advantages of pure Aloha? Of course, we just convinced you that slotted Aloha has the advantage of a higher throughput, and this justifies why this curve is higher than this curve. Intuitively, it provides a justification. However, what we did not see yet is the derivation of the formula itself. S is equal to g e to the power of minus g, and S is equal to g e to the power of minus 2g. This is something that we did not see yet, and this is our next basically discussion, and we will go there, and this will end this video, and then in the next video we will continue with something else. How can we derive the throughput for Aloha, whether pure Aloha or slotted Aloha? Let's revise, let's try to remember together the Poisson random variable. If you have taken random signal theory with me, so it means that I taught you the Poisson random variable. Let x be a Poisson random variable, which denotes the occurrence of a random event of a time during a time interval. So let's say we are waiting at the bus stop for some time, and we are counting how many buses are arriving during this time interval. So we have events of buses arriving in a time interval, or packets basically arriving in a computer network during a time interval, or stations that attempt transmitting frames during a time interval. So what was the meaning of a Poisson random variable? If x is a Poisson random variable that models the number of occurrences, how many occurrences we have in a time interval. Poisson means that the probability mass function is given by the formula lambda to the power of k e to the power of minus lambda divided by k factorial, where lambda is the average number of occurrences during the time interval, during our time interval. In other words, what is the probability that our variable x is equal to value k? What is the probability that our random variable x equals to value k? In other words, what is the probability that the number of occurrences during that interval is exactly equal to k, as long as our occurrences of the event, or arrivals basically, or generation of frames to be transmitted is Poisson. It means that the probability that the variable equals to k is given by lambda to the power of k e to the power of minus lambda divided by k factorial. That k is our variable here, the number of occurrences for which we want to calculate the probability, and lambda is a parameter which is known, it is fixed, it indicates the average number of occurrences in our time interval. So in our basically discussion of the Aloha throughput in pure and slotted Aloha, to derive the Aloha throughput, to derive these formulas, g e to the power of minus 2g and g e to the power of minus g, we make an assumption. We make a simplifying assumption. Let's finish the whole derivation, and then I will justify this assumption at the end. We make the assumption that the number of frames attempted, frame transmission attempts by all stations connected to the network, follow a Poisson distribution. So do we have only one frame attempted? Do we have 2 attempts? Do we have 3 attempts in an interval or in a unit time interval? That number of attempts, of course, is random. It can change from time to time, and we make the assumption that the number of frames attempted follows a Poisson distribution. So the number of frames attempted by all the stations follows the Poisson formula, lambda to the power of k e to the power of minus lambda over k factorial. As long as our occurrence of events represent frame transmission attempts, what is our lambda? Obviously, it is the G. Again, what was the definition of the G, or the offered load? G was, by definition, the average number of attempted transmissions, or the average number of attempted frames per frame time, or in other words, during time t. let's assume that the time to transmit only one frame is capital T. So what is G? By definition, from the definition of G, what was the definition of G again? It is the average number of attempted transmissions during time capital T, the frame transmission time. If this is true, what is the value 2G? What does 2, if I multiply this by 2G, what does it give us? Obviously, it gives us the average number of attempted transmissions in time 2T. Simply speaking, if during time T, G is the average number of attempts, then during time 2T, double of that time, 2G gives us the average number of attempted transmissions, but in time 2T. Now, if we assume that the number of attempted transmissions follow a Poisson distribution, what does that mean exactly? It means that the probability of having k attempted transmissions, the probability of having k attempts in time t is given by g to the power of k e to the power of minus g divided by k factorial. It is exactly the Poisson formula, but instead of lambda, we use g because g is our average. Okay, if the number of attempts are Poisson, but we want the probability that we have k attempts in time 2t, I need that. In my discussion in the next slide, I need that as well. If you have studied Poisson in my random signal theory course, maybe you remember that in Poisson questions, sometimes we have to scale our lambda. So if we have arrivals of buses, follow a Poisson distribution with an average of 5 buses per minute. So lambda is equal to 5 buses per minute. But I need the probability that we have a certain number of buses in 2 minutes. In that case, lambda needs to be multiplied by 2. Again, putting this together, the probability that we have k attempts in time 2t is also Poisson. It follows exactly the same formula. However, lambda is equal to 2g. So we use 2g as our lambda instead of g. So the probability that we have k attempts in time 2t is 2g to the power of k, 2g to the power of k, e to the power of minus 2g divided by k factorial. Whether we look at this formula or that formula, both of them are the same. Lambda to the power of k e to the power of minus lambda over k factorial, but with a different lambda. So in this case, lambda is equal to g itself because we are expressing the probability of having k attempted transmissions during time capital T. And in the second expression, our lambda here is equal to 2g because we are expressing the probability of having k attempts during time 2t. Now, this is all basics. Let me recap. This is all basics. We just assumed that the number of transmissions per frame time follows a Poisson distribution. So it's not only random, but it even follows a Poisson distribution. Having said that, we managed to express the probabilities of having k attempts in time t and the probability of having k attempts in time 2t. Both of them follow the Poisson expression, but lambda is equal to g in the first and lambda is equal to 2g in the second. Now, let's go to pure Aloha. The rest of the argument is really easy. Let's go to pure Aloha and assume that one station has already started a transmission. For simplicity, imagine that I have started transmitting a frame. I have started already transmitting my frame. The question is, what is the probability that my frame is successfully delivered? What is the probability that my frame is successfully delivered in pure Aloha? In pure Aloha, the probability that my frame is successfully delivered, basically, in pure Aloha, is the probability that no other station attempts to transmit anything during the vulnerability period of 2T. That's why I'm saying here the probability that my transmission is successful, the probability of successful delivery is the same as the probability that we have 0 other attempts during time 2T. Why did I use 2T here? Because this is the vulnerability period in pure Aloha. If someone else transmits during this time, we get a collision. What is the probability that we don't get a collision? In other words, what is the probability that we have a successful delivery? Is that we have 0 other attempted transmissions during that time 2T. How can we express the probability of 0 other attempts in time 2T? We just substitute with k equal to 0 in the second expression. Why in the second expression? Because what I need here is the probability of 0 attempted transmissions in time 2t, which is the second expression. Let's substitute with k equal to 0. So 2g to the power of 0, e to the power of minus 2g over 0 factorial, and this is precisely what you see here. Of course, mathematically, 2g to the power of 0 is 1. 0 factorial is also 1, so the probability of successful delivery is equal to e to the power of minus 2g. Don't make a mistake. Is this the throughput? What was the throughput S? The throughput S is the average number of successfully delivered frames. What you see here is a probability. The probability that a transmitted frame is successfully delivered. That's easy. If G is the average number of attempted frames, if we multiply this average by the probability of success for any attempted frame, so the average number of attempts times the probability of success for each attempt will obviously give us the average number of successfully delivered frames, or the average number of successful deliveries, and this gives us S is equal to G e to the power of minus 2G. It means that we have basically derived this formula, S is equal to G e to the power of minus 2G, in pure Aloha. Now, how does slotted Aloha work? In slotted Aloha, assume that we have slotted Aloha, so we have time slots, and stations can start basically transmitting a frame only at the beginning of a time slot. Imagine, for simplicity, that I have started transmitting a frame at a certain time slot. At a certain time slot, I started transmitting a frame already. What is the probability that my frame is successful? It is the probability that nobody else attempts to transmit, but during time t only. Why time t? Because in slotted Aloha, the vulnerability period was only t. If this is my frame, when is my frame successful? If during that time, nobody else attempts to transmit, the vulnerability period was only t. So again, going back to the expression, so the probability that my frame is successful is equal to the probability that we have 0 other attempted frames during time t. How can we express the probability of having 0 attempts in time t? By using the Poisson formula, but the first one here, because I'm talking about time t, so G to the power of 0, because we're just having k equal to 0. G to the power of 0, e to the power of minus g over 0 factorial, and this is what you see here. G to the power of 0, e to the power of minus 2g, times e to the power of minus g over 0 factorial. Again, mathematically, this is equal to 1. G to the power of 0 is equal to 1, and 0 factorial is also equal to 1. So for any frame, if a frame has been attempted, if a frame has started to being transmitted, a frame has started, the probability that this frame is successful is given by e to the power of minus g. We are getting close. However, this is still not the throughput S. Again, the throughput S is the average number of successfully delivered frames. This is the probability that a transmitted frame is successful. So this probability simply needs to be multiplied by the average number of attempts. So average number of attempts times the probability of success for every attempt. It gives us the average number of successfully delivered frames. So in short, S is equal to G e to the power of minus G. So using a simple Poisson assumption, we know, of course, again, to put things together, we know that the number of transmitted frames, G, will change from time to time. So G is the average again. G is the average number of attempted frames. However, the actual number of attempted frames during a frame time will change at random from time to time because stations come and go. Stations have different requirements in terms of transmissions. So we're not expecting that the actual number of attempted transmissions will stay constant. It is basically something random. It's a random variable. And for simplicity, we assume that it is not just random, but it is a random variable following a Poisson distribution. If we make this Poisson assumption, it can be easily shown that for pure Aloha, S is equal to G times e to the power of minus 2G. And in slotted Aloha, S is equal to G times e to the power of minus G. Now, we reached these expressions by a simplifying assumption that the number of attempted transmissions follow a Poisson distribution. It is a simplifying assumption. However, it's a very good assumption. So let me say a couple of comments about this simplifying assumption. First of all, why did we do this analysis here? To compare slotted Aloha versus pure Aloha. So as long as we make the same assumption in both, it is fair. It is a fair comparison. So this is comment number one. Comment number two, basically that assumption leads to a very simplified analysis. So the analysis becomes really easy just using the Poisson expression. If we are not making this simplifying assumption, if we are not assuming that the attempted transmissions follow a Poisson distribution, actually another more involved, more accurate analysis is possible using a technique called Markov chain or using a tool called Markov chains, but the expressions that we reach are surprisingly close to these expressions. Doing that exact analysis is beyond the scope of this course, but I'm just letting you know that if we are not making this simplifying assumption, this Poisson assumption, another more accurate analysis is possible by using Markov chains. However, the expressions that we reach are really close to these expressions. So that assumption is not only fair, it's actually a good assumption. And this will end our lecture, and we will continue the next video with carrier sense multiple access. Assalamu alaikum wa rahmatullah.